Welcome to Tolofsen Physics. So now what we're going to do is we're going to draw a force diagram for something that not every force is perpendicular to each other. And so we're going to look how to handle that mathematically. And so we're going to have some forces that we're going to calculate to try to figure out what's going on. So what we're going to look at is I have a shopping cart, and at least an attempt to draw a shopping cart. And I'm going to push it forward with a constant velocity. However, I'm pushing down on the handle, and that handle has an angle of 30 degrees compared to the ground. So I'm going to push with a 5 Newton force, and let's say the shopping cart is 10 kilograms. So first thing is I'm going to consider, okay, what am I going to look at? I'm going to look at the cart. So I'm going to consider the cart as my system. And so let's draw a force diagram based upon that system. And so the force diagram is going to always have force due to gravity. And why not? Let's go ahead and calculate that right off the bat. So it's going to be 10 kilograms multiplied by 10 newtons per kilogram. And so that'll end up being 100 newtons. So I'll put that right on the force diagram immediately. Okay, well then what else is going on? I'm going to have a normal force. I don't know the size of the normal force yet, and there's a reason for that, and I'm not going to put a number next to it yet. And then I'm pushing downward, and so we're always going to draw our arrows from the center of mass away from it. And that's what the College Board exam will expect as well. So this I'm going to just call my push. So that's a push. And so if I'm moving at a constant velocity, things need to be balanced out. And so, well, what am I doing? I'm actually pushing down a lot, so maybe I should make my force of normal bigger than the gravitational force, and we'll figure that out mathematically in a minute. It's pushing to the right a little bit, so I need some sort of force to balance that out to the left. And so I'm going to call that the force of friction. And we're going to be able to calculate all of these forces. Now, the push force I know is 5 newtons because that's what I measured, that's what I gave you. So now what are we going to do? Well, one way to solve a problem like this is to break this push force into components. And what do I mean by that? Well, first off, I'm going to consider a coordinate system. So I'll draw that in red off to the side. And I'm going to make that coordinate system parallel and perpendicular to the ground. And why am I going to do that? Well, it's potentially going to move in that direction, right? And so if there's a chance that it's going to accelerate along the ground. So if I increase this force, it may accelerate at some point. So I'm going to do that. And why do I do that? Well, the force due to friction is parallel to the x-axis. The normal force and the gravitational forces are parallel to the y-axis. And the only thing that's not parallel to either axis is the push force. But what can I do? Well, I can break that up into two components that follow the x and y coordinate system. So what does that mean? I'm going to draw an arrow so it's just the right length along the x-axis in this case. And then I'm going to draw it straight up and down along the y-axis there. And that gives me a right triangle, right? So I get a right triangle there. And so essentially what I have is I have a push force, I guess I'll write it all the way out, push force in the x direction, and I have a push force in the y direction. So now I can start to figure out what's going on. And now what I have to think about is this 30-degree angle that I drew up here. So that 30-degree angle, if I kind of just put a dotted line, kind of refers to this angle right here. And so that's a 30-degree angle. And I've got two lines, straight lines going through there. So that means 30 degrees exists right there too. So you're going to have to remember some of that geometry knowledge and properties of triangles and lines and stuff like that to figure out your angles. And then you're going to use sine, cosine, tangent to figure out what's going on. So this push is the adjacent, and I know the hypotenuse, right? So technically adjacent, that's cosine theta, I'll just write it in general terms, is adjacent over hypotenuse. Well, how does that apply to this situation? And so what it ends up being is I'll cross multiply this, and it's going to be the hypotenuse, which in this case is 5 newtons, and I'm going to multiply it by the cosine of 30 degrees. And so then that value is what the component in the x direction is. And then I could do the same analysis in the other direction, and that's going to end up being 5 newtons times the sine of 30 degrees. And that's one of the things you got to make sure when you're switching from class to class, that when we're using degrees in this class, typically your calculator is set to 30 degrees. When you use radians in another class, you got to change it for this class. So it depends on what's being given to you. So sine of 30 is half. So technically that equals 2.5 newtons. And then cosine of 30 times 5 is 4.3. So I'm making this very messy, so I might draw a new one. So 4.33. Okay, so let us go ahead and kind of redraw what we have with fewer things on it. And I'll actually make it a lot bigger. So we said the force due to gravity was 100, if I remember correctly. We had this push force, but we're going to replace the push force with these two components. So just to make it a little simpler to read, I'm going to just write force in the x direction and force in the y direction. The push force was 5 newtons, but in the y direction it was 2.5 newtons. And in the x direction it was 4.33 newtons. Okay, and then let me put the other forces in so that we can think about them. So we have the normal force and we have the force of friction. Now this is where writing equations about what's going on in your force diagram is kind of a handy thing, because we've got 2 down forces and an up force. We only have 1 right force and 1 left force. So do I really need to write force of friction equals Fx, which technically was the force push cosine 30. Yeah, that's what that all was. And that ended up being 4.33 newtons. So we know the force of friction is 4.33 newtons. I really should change color, so I will. So for the vertical direction, the y-axis, what we actually have is we have the normal force is my up force, and that is going to equal the gravitational force plus the force that was in the y direction. And I'm going to write it out because y looks like g the way I write it. And so that was sine 30 in this particular case. So what is the normal force? Well, we know the gravitational force based on the information given is 100 newtons. And we also just calculated that the push force in the downward direction is 2.5 newtons. So that means the normal force is 102.5 newtons. All right. So what do you need to do to figure out a problem like this? What you need to do is you need to draw a force diagram. And then what you need to do is, okay, it's balanced. How do I make it balanced? And so generally speaking, I could say all my up arrows equal all my down arrows. And I could separate that out. All my right arrows equal all my left arrows. And if you think about it that way, then we need to take this one arrow that has a little bit of right and a little bit of down, and we need to figure out how much is to the right and how much is down. And then we can say, well, my up arrow equals my 2 down arrows, and my left arrow equals my right arrow. And so basically that is the way we're going to approach pretty much every single force problem that we see. Force diagram, try to figure out, especially when it's balanced, right equals left, up equals down. So we can write an equation from that, fill out what you know, and then you'll be able to solve what you don't know.